Okay guys, welcome back. In this episode we are going to talk about the public key cryptography and how it is being used in the blockchain technology. So let's take a look at the next slide. So in general, cryptography is used heavily in blockchain, especially the two features are the two tools of the cryptography which is heavily used in the blockchain. One of them is the hashing and the other one is digital signature. Hashing is, if you have not watched the previous video on the hashing, you can watch it on my channel. I have already explained the video on how the hashing works and what are the different hashing algorithms used in the blockchain. But in general, the hash can use to verify and validate the data and the integrity check of the data. The other tool of the cryptography which is heavily used in the blockchain is the digital signature. And digital signature is a mathematical algorithm, and that gives the receiver reason to believe that the message was actually sent by the claim sender. So this is just kind of proving yourself or authorizing digitally that you own the asset which you want to transfer, and you sign it by using digital signature. And so this digital signature actually use the asymmetric cryptography, which you also call the public key cryptography, and that's the topic for the video today. So let's take a look at the next slide and learn more about how the public key cryptography works. So before we move forward, I just want to highlight that the digital signature is just like the replacement of your signature on your check. When you're writing a check, put your signature on the check, you authorize for the transfer of the money from your account to someone who is writing the check for. Similarly, just to understand how the public key cryptography works, so I will use this example. Let's say you have the bank card. So your bank card is just like a public key where you have this number which everybody knows, like a bank knows this number. When you go to the cashier, they can see it. When you go to ATM machines, everybody can, this is not a secret. It's printed on your bank card. But your PIN, which only you knows, is a secret, and that will be something like a private key. So this is how the combination of the private and the public key that works together and provide the authorization as a replacement of digital signature when you're writing a transaction on the blockchain. So remember this analogy, and we're going to be using this public key and private key pair as we move along. So just your bank card number is your public key, and your PIN, which is your secret key, which is secret, is your private key. So remember this concept. It's not exactly like this, but it will help you to understand the combination of the public and the private key pair. So let's say if Alice wants to transfer some of the Bitcoin over to Bob. So she wants to transfer 0.01 BTC to Bob. What she's going to do, she's going to provide a signature, and she's going to digitally sign this transaction, and this transaction being sent to the blockchain. So blockchain, if you remember from my previous video on the introduction to blockchain, so blockchain is just like it's a special type of database, no different than the spiral notebook you have, which is kind of ledger. So all the transaction goes into the blockchain. So every page in this notebook is just like a block in the blockchain. So when the transaction goes into the ledger, first of all, it needs to be verified that it's authorized. Yes, the Alice wants to transfer the Bitcoin to Bob, and yes, she has the money in account. So all of this needs to be verified, and the network will verify that it's being digitally signed by the Alice, and it's been authorized. So once it's been authorized, it's going to be transaction hash is going to be calculated, and this transaction goes into the block. So once it's been added to the block, so there will be many different transactions on the block, and each transaction is going to have its own hash. And once all the transactions been written to the block, the hash of all of these different transactions is combined into the page hash, which is the hash of the complete block. And then this hash is also going to be added to the next block. So this is how the blockchain maintain the integrity of the whole blockchain, of all the coming blocks. If anything change in this transaction here, if let's say if later on Alice wants to change this to 0.1 to 0.2 or 0.3, that's going to change this hash, that's going to change this hash, and it's going to change all the hash in the coming block. So as you can see, in order for Alice to transfer the money to Bob, she needs to authorize, and this authorization is going to take in place by digitally signing it. And this is where the public key and the private key comes into the play, and we'll see how that actually really works. It's public key cryptography is a type of system where you have a set of pair of keys. One is called the public key and one is called the private key. So private key is the one which is used to sign and authorize the transaction, and the public key is used to verify that transaction. Or the other thing is, let's say if I encrypt anything with my private key, if I encrypt the message, it can only be decrypted by my public key. Similarly, if message is encrypted by the public key, it will only be decrypted by the private key. So this way you can use one key to encrypt and you can use the other key for decrypt. But these two keys are interrelated. They are mathematically related to each other, but there's no way, if you know the public key, you can derive private key. The other one important thing is, when we are talking about these keys, we're talking about enormous, big, gigantic numbers. So these numbers are pretty much like 100 digit long, or maybe sometimes more than 100 digit long. And just to give you a perspective, total number of atoms is 10 to the power 57 in the whole Milky Way. So now you can imagine how big this number is going to be. So the public key cryptography, the first public key cryptography algorithm is the RSA, which is heavily used, especially if you're using webs every day. So when you see the HTTPS, so that's S is actually secure HTTP, which is based on the SSL and TSL technology, and that's in under the hood is actually using the RSA public key cryptography system. So let's say if I have this message, if I want to send it to computing, first I need to change this text into a number format. And what I use for numbering, so I need to map this text into a number. So I'm just using the ASCII character chart here. The C is represented by 67, so I say, okay, this is my C. O is represented by 111, so you get 111, then you get at M 109, then P 112, and this way you got this big number. So this big number is actually coded computing in by using the ASCII chart. But let's say if you want to send this number, so how the RSA public key work, so you have this message, which is this big number, if you remember from the previous screen, it's a computing. So I'm going to take this number and I'm going to raise it to the power E, or I will multiply this number E times. And then I'm going to perform a modulus N operation on modulus N, which is N is the number. We will talk later on what that number is going to be. And once I do that, then I will get the C, which is let's say this is my encrypted text, and I can go back and change this into using the ASCII chart again and change this into a text format, but let's keep it as a number format here, right? So now I have my encrypted message. I can send it to whoever I want to send it to. Now this is where the magic happens. So they're gonna take this my message and they're gonna raise it to D times. And magically, they're going to do the same thing, the modulus N. And once they perform this operation, magically, it's going to spit out the message M, which is going to be this number, and which can be changed into, by using the text, is changed into the computing. So this is where the magic of the RSA, the public key cryptography system happen, right? So in summary, like in RSA public key cryptography, you have a message M. You're going to raise it to power E. You're going to perform the modulus N operation on it. You will get your encrypted text. Then you're going to take this encrypted message. You're going to raise it to power D, same modulus, and magically you will get the message back. And this is where, as you can see on the numbers, there are some very special magical number here. The E, the D, and N. The combination of these three numbers is providing all the magic. Whereas in these three numbers, the E and E and N are the two numbers which is we call the public key, means they can be shared with the public, everybody knows, and they can use it to encrypt the message. And but we keep the D as a private, and it's a private key, and nobody knows except the user. So if you have this private key, and that's like you have the public key, so people can use your public key to encrypt the message, and you are the one who can decrypt the message. And similarly, if you sign anything with using your private key, then the rest of the public can verify it and can guarantee that, yeah, it is you who actually signed that signature. So this is how the public key cryptography works. So it has a set of numbers. It has two keys. As you can see, these two numbers, E and N are the public key, and D is the private key. So I guess what we need now is we need to know, like, I know you will be thinking how this magic is happening. So it's not actually really a magic. It's basically mathematical computation behind it, right? So there are a few things before we jump into apply this logic or the computation to real numbers and see how it really works. There are a few concepts of the mathematics needs to be understand before we move forward. The first thing is the prime number. So if you have not, I already have a separate video on a prime number. If you want to know more about those prime numbers, you can definitely go and watch that video. But in essence, the prime numbers are the numbers which are only divisible by themselves or 1. So like a 1 is a prime number, 2 is a prime number, 3 is a prime number, 5 is prime, 7 is prime, 11 is prime. So they are only divisible by themselves or 1. Let's say if I have the 8 here, 8 is not prime because 8 is divisible by 4, is divisible by 2, and it is divisible by 1. So it is divisible by more than 1 and itself, so that's why 8 is not a prime number. So the second concept is relative prime. So relative prime means like the two numbers are said to be relatively prime if their greatest common factor is 1. For example, I have two numbers 7 and 9. 9 is not a prime, but 9 is relative prime to 7 because the factor of the 7 are 7 and 1, and the factors of 9 are 3 and 1 and 9. So as you can see, 7 does not share any common factor with 9 except 1, which is okay, and that's what the definition of the relative prime. So we'll say 7 and 9 are relatively prime. Whereas 8 and 10, they are not relative prime because 8 can be factored into 2, 4, and 8, right? And 1, whereas 10 can be factored as 2, 5, and 1. As you can see, 2 is a common factor between 8 and 10. So based on this, 8 and 10 are not common, is not relative prime, whereas 9 and 7 are relatively prime. So I hope you understand the concept of the prime numbers and the relative prime numbers. The other one is the integer factorization. What is integer factorization is like if I gave you this number 36, you can factor these every composite number or any number can be factored into a set of prime numbers. So I can write 36 like 2 multiplied by 2, 4, 4 multiplied by 3, 12, 3 12 multiplied by 3, 36. So now you can break it down 36 into factors. But this integer factorization is a hard problem. It's easier for you to do it because if I give you this number 36, it's easy for you to factor it. But as the number get bigger or the digits increases, it's really hard for you to give me the factor. Let's say it was easier for you to give me the integer factorization of this, but if I give you this number, now it's going to become difficult. Now you used to use a computer, or maybe you need to use a calculator. But even if I keep increasing this number, as I said, if you remember, like these keys are big, enormous, big number. So let's say if I gave you a 100-digit number, then it's going to become impossible even for the computers to calculate that number, or it's going to take a long time for them to calculate the number, maybe a couple of years, right? Or maybe 100 of years, who knows, depending on the processing power. So remember these few concepts, the prime numbers, relative prime numbers, and the integer factorization. That is, the longer the value, the harder and slower this get. So that was the some of the important concepts you need to understand before we jump into the mathematics. The other stuff you need to know, the modular arithmetic. So I also have a separate video in that. But the modular arithmetic is the clock arithmetic, where the numbers wrap around in a circle, and we perform the operation based on that. The circular numbers is a finite field. So let's say, for example, I have this modulo 7 numbers here. So 0, 1, 2, 3, 4, 5, 7. So these are the 6, 7, and then it's going to keep repeating after that. So if I have the 9 mod 7, so I will say is interested in the remainder of the operation. So as you can see, 9 divided by 7, I got the remainder of 2. So this remainder is, we call it 9 mod 7 is 2. So when you combine this modular arithmetic, if you need to know more about the modular arithmetic, you can watch my video on it. I also have it on my channel. It will give you more understanding of this modular arithmetic. But when you join this modular arithmetic with the integer factorization, this is which drive the public key cryptography, especially in the RSA. Okay, so let's keep going with the one last item, and this is the most important part of this whole public key cryptography. It's called the Euler iteration function, which is called phi. Well, the way it is works like the number of positive integers that are smaller than n and relative prime to n. If you remember the concept of relative prime. So let's say I have a number n, which is 8. So I need to find out how many numbers smaller than 8 and they are relatively prime to 8. So if I have numbers 1, 2, I'm going to write them 1, 2, 3, 4, 5, 6, 7, 8. So there are numbers which are relative prime to 8. So 2 is not a relative prime because it's share of common factor. 4 is not because it's not relative prime because share of factor with 2. Similarly 6. So now 1, 3, 5, and 7. These are the 4 numbers which are less than 8, my original number n, and they are relatively prime to number 8. So I will say the phi of 8 is 4. So this is how we calculate this phi function. And then this phi function is really important when it comes to selecting those numbers. If you remember this E, N, and D, which are our public key and the private key. So I hope you remember all of these concepts before we jump into the, and also before we go and try these numbers in real. Okay, so let's go to the next slide. One more thing I just need to emphasize that, like say, if I have a number, let's say, if I gave you the number 8, so you don't, so this is easier for you to find out how many numbers are relative prime to 8 and less than, so you can just write it down and eliminate based on that. But let's say if I gave you the number 1201, let's say 11, now it's going to become harder for you. But let's say if you know this is the prime number, if it's a prime number, then we know that the phi of any prime is equal to p minus 1. So phi function of any prime is easy to know, is just p minus 1. So let's remember this concept here. So we're gonna let's put a star on it because that's gonna come later on and we're gonna discuss that way. Okay, now let's try these numbers in real. Let's see how RSA really works. I think the first step in RSA is initially we pick 2 numbers, and these numbers needs to be prime. For here, just for the sake of simplicity, I'm just using 1 or 2 digit prime, but in reality, these prime numbers are going to be humongous. Yeah, easily 1000 digit numbers, right? But let's say, for example, for the sake of simplicity, I'm just using here very small numbers, 3 and 11. Next, we're going to calculate n. N is just product of p and q. So p multiplied by q, we got 13. Now we're going to find out the phi of n. If you remember, phi of n of any number are the numbers less than n and they're relatively prime to n. So in order to find the phi function of the phi function of the n, we're gonna eliminate all the multiples of n from 1 to 33. So let's say 33, I can write it down like 11 times 3. So 11 and 3 are the factors. So 3 cannot be included in the phi function of 33 because 3 has a common factor with 33. So if 3 is eliminated, then all the multiples of 3 is going to be eliminated. So let's eliminate all those. And 21, 24, 27, 30, 33. Similarly, the 11 is going to be eliminated because 11 is not included. because that's also having a common factor with 33. So now these are the remaining numbers are all the numbers which are less than 33 and they do not share any common factor with 33. So let's take a look at 4. 4 is relatively prime to 33. So if I count all of these numbers, these are pretty much 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. So these are total 20 numbers. So if you remember from previous discussion, like if it's easier for me to find out the phi function of 33 because they're a very small number. But let's say I'm saying in reality these numbers are very big. It's not going to be feasible for me to write it down all numbers and then eliminate one by one. It's a tedious job. It's not going to happen. So, but we know that, and P and Q are also prime. So what we know from the previous discussion, if numbers are prime, then the phi of the prime is always be P minus 1. So similarly, the phi of phi, if my number n is the product of the P and Q, then I can say the P minus 1 and the Q minus 1. So that's multiply. If you do that, like a 3 minus 1 and 11 minus 1, 2 times 10 equal 20. So you can easily find out what's going to be the phi function of n if n is a prime or is a product of the two prime numbers. So that's easier for us to calculate. Doesn't matter how big that number is. So that's pretty important. So now once we have these numbers, so let me erase it first. Let me get rid of all of this. So we have n. If you remember from our previous discussion, our public key is E and N, and our private key is D. So we got our first number n, which is the product of two prime number, and now we got phi of n. That's another number, which is 20 here. So now we need to select our E. So the condition is E must be, or E should be such that it is a prime number, it should be less than phi, and it must be relatively prime to phi. So if I take a look at the phi is 20, so I can pick any prime number which is less than phi. Let's say, just for the sake of simplicity, I'm going to take E as a 3. So if I select E as a 3, which is the prime number, which is relative prime to 20, and is less than 20 also. So this 3 and the n will become my public key. So now we need to find out our private key. So in order to select the private key, which is the D, the condition is if I multiply by D to the E and I apply the modular operation of phi, that's a D times E mod phi, it must be 1. So that's the condition in selecting the D. So let's say for the sake of simplicity, I select the D7. So let's say if D7 satisfy this condition. So D, which is 7 times my E is 3, 7 times 3, which is 21, and my phi is 20. So I am saying 21 mod 20. So this is, let's do the division. 20 times 1 is 20, and my remainder is 1, which is true. So I will select D, satisfy this condition, and I get the remainder of 1. So this D7 will become my private key. So now we got all three numbers. We got our E and N, and we got the number D, which is our private key. So this is how the RSA works in reality. How we select these numbers, how we can generate these, the public key and the private key. The one important thing, for the sake of simplicity, I'm just using very simple number here, the 3 and 11. But in reality, as I said, these numbers are going to be big, and it's going to be very complex to find out E and D. It's not going to be that simple as I have selected here. So let's try this number on a real example. So let's say if I have this message here. Let's say if I want to use this number to calculate and encrypt by using my public key private key. But as I said, I cannot do this because my numbers I have selected is very small. in technical, in real word example, my n has to be way more than my number, the message I'm trying to encrypt. But here my message is too long, so I cannot use these private key or public key pair to encrypt. So what I'm going to do, I'm just giving you a simple number 16. Let's say my message is 16. So I'm going to take the 16. This is my message. I'm going to raise it to the power e, which is my e, if you remember from the previous discussion, right? And I'm going to perform the mod n, which is mod 33. So when I perform this, I will get a number 4. So you can use the calculator to verify this. And then I'm going to send this encrypted message over to the other party. Now they're going to take my encrypted message, they're going to raise it to the power d, which is my private key, and they're going to perform the modulus 33 mod n operation again, and magically it will give you back 16. So now I will say, if you want, you can take any number from 1 to 32, and you can use these public key and private key pair, these numbers, and using the formula of encryption and decryption, you can try and you can see it will work, and whatever message you encrypt, you will be able to decrypt by the private key. So this is how the public key cryptography system works, and I know the math is really magical here. Okay, so let's summarize the summary of the public key crypto system. It uses the pair of keys, the public key and the private key. Public key is something which you can share with everybody, and the private key is something which you keep secret to yourself. Anybody can encrypt the message by using your public key, and they can send it to you, and once you receive it, you can decrypt it by your private key. So once somebody encrypt this message with the public key, nobody else in the world can see it except the owner of the private key. Similarly, I can sign any document, or I can sign any transaction by using my private key, and it can be verified by my public key, and it will verify that yes, the transaction is actually authorized by the holder of the private key. There are two major family of the public key crypto system. One is the RSA, which we just discussed previously. It is based on the discrete logarithm problem. And there's another one, elliptic curve digital signature algorithm, which is based on the elliptic curve cryptography. We'll have a separate video on elliptic curve later on. Elliptic curve crypto system is considered most secure, and then RSA, and most of the blockchain, especially Bitcoin and Ethereum, they use ECC as a public key crypto system, and especially the digital signature algorithm. I hope you like the video. I know it's a little bit the complex topic, but I try to make it simple. And in the coming videos, we're gonna discuss more about the digital signature and also the elliptic curve cryptography and how it's been used in the Bitcoin and the Ethereum.